Okay, today we want to talk about the derivatives of inverse trig functions. We've already learned the derivative of the 6 basic trig functions, and today we're going to learn the derivative of all 6 inverse trig functions. So let's start by proving them, just in case we forget them. We want to prove that the derivative of the inverse sine of x is equal to 1 divided by the square root of 1 minus x squared. So we're going to start by basically letting y equal inverse sine of x. And we want to take the derivative of this. However, we don't really know, obviously, what the derivative inverse sine of x is, so we are going to take the sine of both sides. So when we take the sine of the left side, it just becomes sine of y. When we take the sine of the right side, the sine and inverse sine cancel, leaving you with simply x. Now we're going to take the derivative of both sides using implicit differentiation. So we're going to take the derivative with respect to the letter x. Well, we're going to take the derivative of sine, which is cosine. We're going to leave the inside function alone. And then we're going to multiply by the derivative of the inverse function, which is y prime, which we could write dy dx either way. And the derivative of x is just 1. So we have come to the conclusion that y prime equals 1 over cosine of y. Now this doesn't really help us yet because dy dx, the derivative, is still defined in terms of y. So what we'll do is we will, over here, we'll make a triangle. And tell you what, why don't we make a triangle. And we'll make a triangle, doesn't really matter, put it in the first quadrant. And we will remember that it says sine of y equals x. I'm going to write this as x over 1. So sine of some angle y, I'm going to write the angle y right there. This is the opposite over the hypotenuse. So x over 1. If we do the Pythagorean theorem, we will get this side of the triangle to be the square root of 1 minus x squared. Now we're able to express the cosine of y as the adjacent over the hypotenuse. So y prime is equal to 1 over square root of 1 minus x squared. All right, if you're watching this video, I want you to see if you can try to do the other two proofs. Okay, here we want to prove that the derivative of the inverse tangent is 1 over 1 plus x squared. So we're going to use that same method. We're going to let y equal the inverse tangent of x, which is essentially the function we're trying to take the derivative of. So we are going to take the tangent of both sides. So tangent of y equals x. And then we're going to use implicit differentiation. So the derivative of tangent is secant squared y. And we're going to leave the y alone. Then we're going to multiply by the derivative of y, which is y prime. And the derivative of x is simply 1. So y prime is equal to 1 over the secant squared of y. All right, so over here, we have already established that the tangent of some angle y is x over 1. Maybe I'll write that, x over 1. So I'm going to draw a triangle here. And we will label this triangle with the proper sides. So we will label this triangle as the opposite over the adjacent. So the opposite over the adjacent. And if we do the Pythagorean theorem, we will get the square root of 1 plus x squared. All right, so the secant is the hypotenuse over the adjacent side. The hypotenuse is root 1 plus x squared over 1, the adjacent side. But when you square that, it's going to end up giving you y prime is equal to 1 over 1 plus x squared. All right, I'm not going to do example 3 because I think you can see how it's done, and I want to shorten this video so you can try that on your own. Okay, here we have a table of the derivatives of all 6 inverse trig functions. And what we notice here that's different is that these derivatives are taking into account that the u is not necessarily always x. It's taken into account the chain rule already. So it's saying that u could be anything. Could be 3x, could be 4x, could be 5x. So let's just take this first one, for instance. The inverse sine of u, the derivative of that, is u prime, the derivative of u, and the square root of 1 minus u squared. So the first thing you want to do for letter A is identify what is your u. Well, it's pretty simple. U is what you're taking the inverse sine of. So u equals x over 3. So u prime is going to be the derivative of this, so just 1/3. And so what we have here is 1/3 over the square root of 1 minus, and u is x over 3, so I'm going to square that, x squared over 9. Now what we want to do now is we actually want to factor out a 1/9 here, and running out of space a little bit, but we want to basically factor out a 1/9 inside of the square root. And that's going to leave us with 9 minus x squared. And make sure that makes sense to you. So if you distribute the 1/9 back in, 1/9 times 9 is 1. 1/9 times negative x squared is negative x squared over 9. Then you can take out a 1/9, and it's going to come out of the square root as a 1/3. That 1/3 is going to cancel with the 1/3 on top, leaving you with a final answer of 1 over the square root of 9 minus x squared. And I do apologize for not leaving a lot of space on this problem. All right, letter B. This one's much easier, much shorter. The derivative of cosecant, inverse cosecant of x cubed. And once again, we have negative u prime. Our u is x cubed, so negative u prime is simply going to be negative 3x squared over the absolute value of u. U is x cubed. And this is going to be times the square root of u squared. So x to the 6th, because when you square x to the 3rd, that's what you get, minus 1. And the best we can do here is simply cancel off the x squared. Going to cancel off an x squared there, leaving you with an x, and your final answer is going to be negative 3 over x square root, and we'll leave this in absolute value, square root of x to the 6th minus 1. All right, let's move on to the inverse cotangent. Same type of thing, you're just following the formulas here. Negative u prime. Well, u is 2x, so u prime would be the derivative of 2x, which is just 2. So it's going to be 2, negative 2, over 1 plus u, which is 2x, squared, which is 4x squared. Very easy. Inverse tangent. All right. So now we're going to do u prime. So now we're going to have to do a little bit of work because our u is the square root of x. So our u prime, if we take the derivative of this, is going to be 1 over 2 root x. So let's go ahead and put that on our numerator here. So it's going to be 1 over 2 root x. And this is all going to be over 1 plus u squared. U is root x. When you square that, you get x. All right, and essentially, done. I'm going to multiply the top and bottom of this fraction by 2 root x, and that way it's going to cancel here, leaving us with 1 over 2 root x times 1 is 2 root x. 2 root x times x gives me 2x to the 3/2 power. Okay, as everything else that we've done, we have something that's asking us to find a tangent line to the graph. So that means we need the point and the slope. So let's start with the slope. We are going to say, okay, y is equal to inverse cotangent of x. And so our y prime is going to be negative 1 over 1 plus x squared, and that's from our table. So we can actually plug in our negative 1 into our derivative to get our slope. When we do that, we're going to get negative 1 over 1 plus 1, which is 2, so there's our slope. Now we need to plug negative 1 into our original function to find our y, then we can write our tangent line. So our y is equal to the inverse cotangent of 1. Now what this is basically saying is there is some angle on the unit circle where the adjacent side over the opposite side is 1. So for this, we need to know what quadrants the inverse trig functions are operating in. So inverse sine, if you can remember from pre-cal, is going to be quadrants 1 and 4. Inverse tangent is the same, 1 and 4. The inverse cosecant, because it's related directly to the sine, is going to be 1 and 4. Now inverse cosine, if you can remember from last year, is quadrants 1 and 2. That makes the inverse cotangent 1 and 2. And the secant, inverse secant, is going to also be 1 and 2. So if we're looking for, actually this should be negative 1, actually. If we're looking for the angle that has an adjacent side of negative 1 and an opposite side of 1, for the cotangent, we will put it in quadrant 2. So we're going to make a triangle in quadrant 2. So here is our triangle. We're going to make our adjacent side negative 1, our opposite side 1, and then our hypotenuse will be root 2. So we can see that this is going to be 135 or 3 pi over 4. So our x is negative 1, our y is 3 pi over 4. So we can do y minus 3 pi over 4 is equal to our slope, negative 1/2, times x minus a minus 1, which is x plus 1. So basically, we're doing the same thing that we've done in other sections of the book, except now we're applying it to inverse trig functions. Okay, we're going to review inverse trig functions and how they work just for a moment so we can be a little bit more successful on some other problems here. We're going to evaluate the sine of the inverse cosine of 4 over 5. So essentially, when we say the inverse cosine of 4 over 5, what we're basically saying is there is some angle, and we'll call that angle theta. There's some angle theta where the adjacent side is 4 and the hypotenuse is 5. Of course, we know that is going to be 3 because of the Pythagorean theorem. So this is the theta. Anytime you do an inverse trig, you are looking for the angle. So this is the angle. Now, the sine of whatever this angle is, we don't know what it is numerically, but the sine of whatever this angle is going to have a ratio of opposite over hypotenuse. So 3/5. All right, so once again, inverse cosine of 4/5 means there's some angle, we don't know the numerical value, that has an adjacent over hypotenuse of 4 over 5. We can fill in the other side by Pythagorean theorem, and we can say the sine of whatever this angle is opposite over hypotenuse. All right, let's apply the same thing here. So we're going to make an xy axis, and we will say that we have the secant, the inverse secant of 2x. That means that the hypotenuse, I'm going to make this 2x over 1, the hypotenuse over the adjacent, that ratio, hypotenuse over adjacent, is 2x over 1. So here we have some angle theta, and if we do the Pythagorean theorem, we will get the square root of 4x squared minus 1. All right, so now we can say, well, the tangent of this angle is opposite over adjacent. So simply going to be 4x squared minus 1. Let's apply the same idea to this one as well. So we are going to say that the inverse cotangent, all right, that means that there's some angle where the adjacent over opposite, because we know tangent is opposite over adjacent, so the adjacent over the opposite is 1 over 2x. So we're going to take the square, we're going to do the Pythagorean theorem, and we're going to get 1 plus 4x squared. Let me make that a little bit nicer. 4x squared. So the cosecant is the hypotenuse over the opposite. The hypotenuse over the opposite side. All right, now we're going to see how this works on a couple of actual calculus problems. Okay, here we see the beauty of being able to simplify these inverse trig functions, because let's say we were asked to find the derivative of this. We would have to use the chain rule. We would have to take the derivative of secant, which is secant tangent, but it would be secant of this, tangent of that, and then we'd have to take the derivative of the inverse tangent of 3x, which is actually 3x inside of inverse tangent, and it would get really, really messy. So the question is, can we simplify this so that we can take an easier derivative? That's what we want to do. So let's see if we can do that. Let's go ahead and make a triangle. And let's say that the inverse tangent of 3x means there's some angle theta that has an opposite side over an adjacent side, because we'll make this 3x over 1. So an opposite over adjacent, that's going to be the tangent of some angle theta. When we do the Pythagorean theorem, this is going to give us 1 plus 9x squared. Now, what is the secant of that angle? Well, the secant of the angle is going to be hypotenuse. So we can basically simplify this to be the hypotenuse over the adjacent. All right? So now, look how much easier our problem has become. We're now simply trying to take the derivative of the square root of 1 plus 9x squared, which we can write as 1 plus 9x squared to the 1/2 power. Now we can say, by way of chain rule, we can say 1/2, leave the inside function alone, drop the power down, and then multiply by the derivative of the inside, which is 18x. And man, look at how much easier that derivative was just by using some inverse trig. 18 and 2 are going to cancel off and give us 9. So 9x over the square root of 1 plus 9x squared. And that is the beauty of being able to recognize that you can simplify these very complicated functions using inverse trig. Okay, which of the following is the slope of the tangent line to this curve at x equals 1? So we just need to take the derivative, a simple derivative. So y prime. So we remember that the derivative of the inverse tangent is u prime over 1 plus u squared. It's going to take a moment to get these committed to memory, but our u is 2x, so u prime is the derivative of 2x, which is 2 over 1 plus u squared. Well, that's going to be 4x squared. And now all we do is we plug in our 1 into our derivative, and we get 2 over 5. So the answer is C. All right, last example here. We've got a particle that's moving along the x-axis. So its position at any time t is x equals arctan, which is another way of saying inverse tangent. And we want to prove that this particle is always moving to the right. So we will say dx dt, which is essentially the change in the x position or horizontal position as time is changing. Well, we know that this is going to be 1 over 1 plus t squared. Now, we can prove that it's always moving to the right because no matter what value of t that you plug in here, it's going to be squared, which makes it positive. You add 1, it's still going to be positive, and 1 over any positive number is a positive number. So you'll have to say something like, for all values of t, you'll say x prime of t is greater than 0. So therefore, particle is always moving to the right. Okay, now we want to prove that the particle is always decelerating. In part A, we proved that the derivative is 1 over 1 plus t squared. So now we need to find the acceleration. We've already found the velocity, so we're going to say the acceleration is equal to the derivative of the velocity, which we could use the quotient rule, but we're not going to do that. We're going to rewrite this as 1 plus t squared to the negative first power. We're going to basically move this whole denominator up to the top and make it that. That way we can use the chain rule. So negative 1, leave the inside alone, drop the power down to negative 2, and then we're going to multiply by the derivative of the inside, which is 2t. Let's go ahead and write this as negative 2t over 1 plus t squared squared. Now, for any value of t that you plug in here, you're going to get a positive number inside these parentheses. And then when you square it, it's going to be positive. And for all t that is greater than 0, so we're only looking at positive time, obviously, the numerator is always going to be negative. So you're guaranteed to always have a negative number on the top divided by a positive number on the bottom. Therefore, it's always decelerating. Okay, for this last part, we are basically trying to find what is the limiting position of the particle as t approaches infinity. So basically, we're trying to find the limit as t approaches infinity of our function inverse tangent of t. For this, it would be helpful for us to recognize or to remember what the graph of the inverse tangent is. So the inverse tangent actually has two horizontal asymptotes, and it's stuck between here. The reason is because the regular tangent has vertical asymptotes. All right, so essentially the inverse tangent looks something like this, and the horizontal asymptotes are located at pi over 2 and negative pi over 2. So as t approaches infinity, the y value of this function will never ever get bigger than pi over 2. It actually will never equal pi over 2. It just gets closer and closer to pi over 2.